We should be in business. So today we just took our first quiz. It is just a quiz. If there's something you missed here or there, don't fret too much. It's intended to be more of a checkup, see how you're doing. And so I wouldn't, again, that's sort of the purpose of these things. And there will be a lot of quizzes throughout the semester. We're pretty good at being able to stay on tack and on time in this course. It's not quite as crammed as some of my other courses. And so as a result, we should be able to do quizzes for most of the chapters. So there will be many of these. So today we're going to be doing and focusing on Chapter 3, and hopefully we'll get mostly done with the lecture slides for Chapter 3, at which point we'll be ready to talk about the homework on Monday. The homework, I forgot to print the thing off for you, but it is on Blackboard, so you can print it for yourself. So if we go to Unit 1, Neurons, go into Chapter 3, Neuronal Membrane at Rest. The homework is right here, so just download the thing, print it, and then I do want you to complete this in hard copy and bring it to class on Monday, along with a copy of it, like a photocopy of the thing. Because most of this, you don't want to be doing this on the computer screen probably, unless you've got like one of those styluses, which maybe you guys do now. You've got the whiz-bang computers. But we on our old computers can't do that as easily. And furthermore, I mean, again, I just think this is, a lot of times when you're doing problems, you're doing math, it's easiest just to write this stupid thing out in long form. So please do complete this. I will be grading it for accuracy. So bring a copy so that we can then talk about it in class, though, and actually get something out of it if you struggle. The goal for today is basically to introduce the stuff you need to know in order to complete this homework assignment. So we need to make sure we get through that batch of material. Okay. So I think where we ended last time is we were talking about this situation where as we're tracking movement of ions across membranes, what could happen if you get a situation where a membrane is permeable to a cation, but it's not permeable to an anion, or it could be vice versa, but this is our example that we're working with here. So in this case, this membrane has a channel that's open that allows potassium ions to flow freely across the membrane. But this anion here, this could be like proteins that often have negative charges. This guy cannot actually flow across the membrane. And as a result, it's basically just sort of stuck or parked there. In this case, what will happen is the potassium ions will diffuse across the membrane, and you'll get this sort of congregation of positive charge right along the inner surface of the membrane. It's not a massive charge difference in terms of what you might see in, like, if you're doing electrical engineering and you're dealing with volts, like full volts of difference. But it is a bit of a charge difference, and the positively charged particles will tend to be directly interacting, almost like magnets, across that membrane with the negatively charged particles that are left on the other side of the membrane. That charge difference, though, that's what we call a membrane potential. So that's what we're trying to understand how these things, how these work. So what happens next? The idea here is that these potassium ions would continue to stream across this membrane because they're moving down their concentration gradient. And as they do so, they're going to be adding more and more positive charges over here. But a thing will happen is that as you continue to add positive charges to that side of the membrane, you will get to a situation where there's so much positive charge over here, that positive charge on this surface of the membrane starts to conflict or interact with more positive charges coming over. So you guys know about charges and how charges interact with each other. What happens when you put same charges together? Like, what do they tend to do? Yeah, they tend to repel each other, right? So opposite charges, positives and negatives, they'll be attracted to each other, and that's what's happening across the membrane here. But the positive charges that are on this side of the membrane are now going to be repelling any new positive charges that try to get across. So you have a concentration gradient effectively pushing or driving potassium ions to go this way, to the right. But then what will happen is that this electrical gradient that's set up by the charge now that's accumulating on this side of the membrane, these positive charges will start to push and repel the potassium ions back the other way. And you will get to a point where the rate at which potassium ions move down their concentration gradient is exactly offset by the rate at which they're being repelled and pushed back out of the membrane via this electrical gradient. Okay? So that's what all these words say. Potassium ions will continue to stream out of the cell, adding more and more positive charges to this side of the membrane. until there is so much positive charge along the outside of the membrane that it starts to repel additional potassium ions because they are positively charged, and it's positively charged out here. And at the same time, you've got negative charges on this side of the membrane that would be attractive to the potassium ions. So potassium ions come over here, and all of a sudden they're being repelled by potassium and attracted by these anions, and so they may be basically swept back to the other side of the membrane. So eventually you'll get to the point where even though the concentration gradient still exists, the concentration gradient is balanced or opposed by the electrical gradient, and you'll get to a point where there's no net movement of potassium across the membrane. So there's equal numbers going from the left to right as there are going from the right to the left. Does that make sense? This is a really important point. So at this point now, we have effectively, even though the concentration gradient's still there, we have reached equilibrium because the concentration gradient is fighting the electrical gradient and vice versa. They are opposed to each other. So at that point where we've reached equilibrium in terms of movement of potassium ions, we call that point, that memory potential, so that charge difference that allows you to be in equilibrium, we call that an equilibrium potential. And it's a really cool and important number because if you start in a situation where there's a concentration gradient and a difference in permeability in your ions, and you'll start to have ions moving across the membrane, and they'll keep going until they get to that equilibrium potential. And so this is sort of a stable state at this point, where for a given concentration gradient, we should be able to predict that there's a specific membrane potential at which we'll get no net flux across the membrane. And the membrane will basically be pushed until it gets to that particular memory potential by the flow of those ions. I might have lost you in the last little bit, but that's the idea. So the memory potential at which there is no net movement of ions is called the equilibrium potential of that membrane. All right, there's an animation here. I'm going to try to play it. Oh shoot, I didn't download it. All right, I'm not going to be able to do this right now. I will try to play this for you the next time. This is on the electronic materials that came with the textbook if you bought a new one. It's not essential. It just sort of illustrates that same point that we just did again, but I have some other activities. I should have gotten logged in and I forgot to do it. Okay, so this is this concept of equilibrium potential. It's the memory potential at which you have basically equal force caused by the concentration gradient and the electrical gradient. So another way to put it is it's the memory potential at which you have the concentration gradient perfectly balanced by the electrical gradient across the membrane such that you're in equilibrium. You have no net flux of ions across that membrane. We can figure out, at least just qualitatively, just by looking at the thing, we can figure out what direction or what that memory potential will be just by looking at the concentration gradients and figuring out which way ions should initially flow, right, before there's any kind of an electrical gradient. So here's my question to you. So here is a cell. There's, you can think of it as like taking a slice through the axon. So we'll have the inside of the cell and the outside of the cell. So I always draw these things just as little circles to make it easy for me. So what do you think will happen if there is I'll do this one for you and then I'll give you some other ones to work on yourself. So if there's high extracellular sodium concentration versus low intracellular sodium concentration, so there's much more sodium outside than inside, and then we open a sodium channel, what should happen to the inside of the membrane? What should the charge become on the inside of that membrane? And so first of all, which way should sodium go? Should it come out of the cell or into the cell? Yeah, it should go in, right? So sodium is a positively charged ion. It says it right there. So because sodium is a positively charged ion, positive charges then are traveling across this channel. So what should happen to the inside of the membrane? Should it become more positive or more negative? More positive. Yeah, that's all there's to it. We're going to quantify this in a little bit, but this is sort of like the basic thing. So, and it should become positive on the inside of this membrane until such time that the positive charge is sufficient to balance against this concentration gradient, And at that point, then you'll have equal numbers of sodium ions being repelled from the inside and attracted to the outside of the membrane. And so at that point, we'll hit an equilibrium. But that should happen with a positive charge on the inside of the cell. That's what that tells us. Okay? So we could predict from this little illustration that, put it this way, so we would predict that the equilibrium potential should be positive, right? So we always remember, and this is a key thing, so we always measure membrane potentials on the inside of a membrane. That way we sort of, usually what you do in practice is you poke, this is supposed to be an intracellular electrode. So it's a little glass electrode. You poke it into the inside of the cell. That way you know where you're recording from. And so we always measure membrane potentials on the inside of the cell. So in this case, the inside of the cell's membrane, which is what we would measure as a membrane potential, should become more positive if we open sodium channels and there's a high extracellular sodium concentration and low intracellular concentration. That'll make sense? So try it yourself. So I gave you sodium. What should happen if you've got high extracellular calcium concentration? And what should happen if you've got high extracellular chloride concentration? So just take a second, work through the same thing. Okay, so let's start with calcium. So calcium, I said there's high extracellular calcium concentration. So if we open a channel for calcium and allow it to flow down its concentration gradient, what should happen to the inside of the membrane? Positive, negative? What'd you say? Just shout it. Yeah, positive, right? So positive charges, this is just like sodium. The only difference is that calcium's got a double positive charge here. So it's a little bit more positively charged, which means it'll cause the change in membrane potential to swing more quickly, at least on a per calcium ion basis. But it's the same thing. It's positively charged stuff going in, which will make the inside of the membrane more positive, until such a time that the positive charge inside is sufficient to start repelling calcium ions out at the same rate at which they're moving down their concentration gradient. And at that point, you'll be in equilibrium. So here we'd expect the membrane potential to become more positive, and we predict then the equilibrium potential should be positive. That's the membrane potential we need to have that balance between concentration and electrical gradient. That's called the equilibrium potential. So it should be positive. Here, chloride ions. Again, I've said they're high extracellular, low intracellular. So if they're moving down their concentration gradient, how should the membrane potential change? Positive, negative? I heard somebody say negative. Yeah, so they're high concentration outside. So they'll move down their concentration gradient. These are negatively charged ions. So because they're negatively charged ions, they'll make the inside of the membrane more negative, which conversely will make the outside more positive because they're little negative charges going in. And they'll keep going in until such time that the membrane potential gets so negative that it starts to repel them, and they're attracted out by the electrical gradient at the same rate at which they're moving in on the concentration gradient. Here's the last one. This is sort of what we just did before on the prior slide, but I don't want to actually write it up here. So here we've got potassium ions. Potassium tends to be high concentration inside instead of high concentration outside. So in this case, we've got a high concentration inside, low concentration outside. Potassium ions should move down their concentration gradient, which will make the outside of the membrane more positive, but we measure it on the inside all the time. We always measure on the inside. So the inside of the membrane here should become negative, right? And that's what typically happens with potassium. So all you really need to know to predict which direction or how the membrane potential is going to change is, first, which direction is the ion moving? And it's going to move, at least initially, it'll move based on its concentration gradient. You also need to know the charge of the ion, right? So if it's positively charged, you can see that going one way, it'll cause it to become negative. Going another way, it'll cause it to become positive. If it's a negatively charged ion, even if it's going into the cell, this guy is negatively charged and it causes a negative membrane potential. Here, these two are positively charged going in. They'll cause a positive membrane potential. So you need to know which way it's going, which is basically given by the concentration gradient, and you need to know the charge of the ion. Sound good? One of the first questions on the homework asks you basically just to do this. So I give you some concentration gradients. Your job is to draw an arrow and indicate, is the membrane going to become more positive or more negative? And again, it's always the inside that we're measuring. So the inside of the membrane, is it going to become more positive or more negative as a result of that movement of the ion? And that's all you're doing in the first, there's a bunch of little circles. You just draw a little arrow and put a plus or a minus sign. Okay? Now, I just said, all we need to know then, to know the membrane potential, or at least the charge, you know, a plus or a minus of the membrane potential that will occur, is the concentration gradient and the charge of the ion. So that actually starts to help us build an equation. And that equation is the Nernst equation to actually quantify, like not just is it a positive or negative number, but what is the actual charge value that we're dealing with here. So the equation is called the Nernst equation, and it looks a lot worse than it is, but it's basically an equation that allows us to calculate the equilibrium potential. So the equilibrium potential is that membrane potential at which there's an equal balance between the concentration gradient and the electrical gradient. I'm repeating myself a lot, but that's on purpose because these are critical concepts. So it's going to depend on the concentration gradient as well as the charge of the ions. Larger concentration gradients will require a larger potential difference, a larger electrical gradient effectively, to oppose it. Different charges of ions cause differences in the electrical potentials. So here's the equation. The equation reads, and this is at 37 degrees C, which is our body temperature. We will never in this class violate that. We're always going to assume 37, so you don't have to worry about that. You just, I mean, you can be aware that this constant depends on that number. But basically, this is saying the equilibrium potential of the ion, which is the E ion number. E ion, the equilibrium potential for a given ion, is dependent on this constant, which is based on empirical work, divided by Z. Z is the charge of the ion. So if it's a sodium ion, this is +1. If it's a chloride ion, this is -1. If it's a calcium ion, it's +2. Okay, so that's just the charge of the ion, times the logarithm of the concentration of the ion outside the cell divided by the concentration of the ion inside the cell. And it's, you know, I know there's a log thing there. It's really not that bad though. So what I'd like you to do is actually try this. So I'll rewrite the equation here. And again, you can use your phones. This is a good time to learn how your log button works. So I'm going to give you these concentration gradients. So there's potassium, sodium, calcium, chloride, the same ones we just did here. Here are actual concentration gradients derived from empirical studies for a given neuron. So the concentrations are all given in millimolar here. You'll note that it's a millimolar divided by millimolar, so that kind of cancels out those units. And the only other unit thing here, the Z is unitless. The only other unit is this millivolt constant, right? So your answer should be in millivolts. So I'd like you to try to calculate the equilibrium potentials for each of those 4 ions using this equation, this Nernst equation. Okay? I'll give you like 5 minutes to work on it. Oh, let me just say, so if you have a calculator that's kind of like, the graphing calculators are delightful. So graphing calculators, you just type in 61.54 divided by Z times logarithm, and then you put this in parentheses, and that's great. And some calculators, I have another calculator that's like halfway between a graphing calculator and the traditional calculator. I can also type it in that sequence. If you are using your phone or you have more of a traditional old style calculator, what I have to do is I have to basically work backward. So in that case, I go concentration of ion out divided by concentration of ion in, and I hit enter, and I get that number. And then to take the logarithm of that number, I hit the log button, and that'll give me all of that. And then I can multiply by 61.54 and divide by z. So if you have trouble, you have to figure out how your calculator wants that input. Okay, but if you have, if you're using your iPhone at least, the standard calculator in there, you get this number first, and then you hit the log button of it. So it's sort of working backwards. I did that wrong. I didn't. I'll give you another minute or so to work on them, but then we'll do one. We'll call it answers too. So for the first one, for potassium, so I'm just rewriting that formula, but I'm plugging in the numbers. So this says the equilibrium of potassium ion, instead of the ion there, it would be equal to 61.54 millivolts divided by the charge Z, which is +1 for potassium, times the logarithm of the concentration outside, which is 5 millimolar, divided by the concentration inside, which is 100 millimolar. Okay, so that's the setup. So when I typed that in on my iPhone, I typed 5 divided by 100, and then I hit the log button after I hit 5 divided by 100, and then I hit enter, or equals. Then I hit the log button. Then I multiply by 61.54, and just because this is the way my brain works, I like to be OCD, so I divided by 1. Which you don't actually have to do, but I did. And I got, what did I get? I got minus 80 millivolts. Did you get minus 80 millivolts? Okay, if you did not get minus 80 millivolts, make sure you know what you're doing with the log button here, and I can try to help you. Yeah. Yeah, usually like a tenth is plenty. Usually we're dealing with like whole millivolt values is all we really need. I don't know, I have a habit of rounding to the 10th. if you want to be like, you know, actually use significant digits, you can. But I think, you know, I don't know. Then you'd only be using 1. I would usually go to the 10th at most. I'm not real picky about that, you know. What'd you get for sodium? I mean, sodium's set up the same way, just with different concentrations. It'd be 150 over 15. So what'd you get for sodium? Let me just shout it. Yeah, it actually works out. It's log of 10, I think, so you get 1. So it's plus 61 point, I'll say 0.5 millivolts. That works. Calcium. What'd you get? Yeah, I'm just going to say 123. If you got 250-ish, that means you didn't divide by 2, and the charge on calcium is plus 2. And then chloride, you have to divide by -1 on this one, but it should be like minus, what? I got 66, I think, but maybe I mistyped something. I don't know. Yeah, that's about right. Okay, so the question is, what does this number that you're calculating mean? So here we calculated minus 80 millivolts. What is that? Anybody? What do you think that means? Go there. Yeah, so this is the actual memory potential. So when you're measuring something in millivolts, that's a charge. That's looking at a charge difference. And this is saying that there's an 80 millivolt charge difference basically across the membrane. And it's negative on the inside of the cell. And you will note, right, that the sign that we predicted for the inside of the cell matches the sign that we just calculated. This is a great way to check your work, at least in terms of signage, is you can make sure that what's, you know, you just sort of qualitatively think is happening here matches the number that you get here. Similarly, we predicted a positive equilibrium potential for sodium here because sodium's moving in, because it's high extracellularly, and that's very much what we got. This is the actual memory potential at which the concentration gradient that we're given will be balanced by the equilibrium potential, or I'm sorry, the concentration gradient will be balanced by the electrical gradient. And then similarly over here, this is the same thing for chloride. It's negative, right? Because we expected it to be negative. Same thing happened with calcium. So we're just sort of quantifying what we've already done qualitatively. And this is telling us this is the memory potential at which we'll get a perfect balance between concentration gradient and the electrical gradient. Okay? So some additional things so you understand how this thing works. First, very small concentration changes are required to create biological memory potentials. So, you know, we said, and you might think, and this would make sense, right? I'm giving you effectively initial concentrations, and to get the charge to change, you should expect to see ions moving across the membrane, which means the concentration should change. And it's true, the concentration would change, but it doesn't take much. So you might shift from 100 millimolar to 99.99999 millimolar in order to cause a membrane potential to shift from 0 to minus 80 millivolts. It's almost a negligible amount of ions that actually would move in that case, in terms of what we would actually calculate and be able to measure. So you can treat those concentrations as constants for any of these problems we're doing. Yes, technically they move, but they're moving in a, they're shifting in a very, very small amount. So that's one thing. Another thing is we shouldn't say once the particles enter, they only cluster along the inside of the membrane and they interact across the membrane like magnets. So you shouldn't say the entire solution on the inside or outside of the cell is charged. It's really just right along the edge of the membrane. So we would say the inside of the membrane has a charge, but we wouldn't say the entire inside of the cell is charged, right? And that's what this illustration is showing. There's basically equal charge everywhere except for right along that membrane. Finally, there's a neat thing that happens where as long as the larger the difference between the equilibrium potential, which is the point at which you get no net movement, and the actual current membrane potential, the bigger that difference, the faster ions move. So that means that if you're starting from 0 and moving all the way to plus 61, in the case of sodium, initially ions would be pouring across because there's a big difference between a 0 memory potential and a 61 memory potential. But you gradually would be raising that memory potential, and when it gets up into like, plus 55 millivolts, very few sodium ions would be trickling across at that point. So we can call this difference between memory potential and the equilibrium potential of an ion, we call that the ionic driving force. And as long as there's a difference there, you'll get movement of ions. The bigger the difference, the larger the flow of ions. And what should happen when your memory potential equals the equilibrium potential of the ion? Like, what should happen to the ion at that point? Is it moving? Yeah, there would be no net flux of the ion at that point, right? Because your memory potential, which is Vm, equals the equilibrium potential of that particular ion. All right. Okay, so what determines the memory potential in cells? So here's the thing. We're dealing with kind of an artificial situation in all those calculations where only one ion is able to get through the membrane. And usually that's not true. Usually what happens is you've got multiple permeable ions. So if you had a situation where the memory was only permeable to potassium, for example, in that case, then the memory potential is going to change until it equals the equilibrium potential of potassium, which would be minus 80 millivolts. However, most of the time, we've got another situation where, we've got a situation where both potassium and sodium channels might be opened at the same time. So what do you think is going to happen to the memory potential if at rest, potassium allows a minus 80 millivolt memory potential, but sodium allows a plus 62. If you open both channels, where do you think the memory is going to end up? What do you think? I mean, you don't have to quantify it, but like, what do you think? Why negative? Because this one's bigger than this one? Or, yeah, probably not very negative, right? I mean, you'd expect to be somewhere in between. These two effectively would be fighting each other. So they would be competing for the memory potential, you can think of it. So if these are equally permeable, you'd expect the memory potential to be, somewhere pretty close to neutral. Maybe a little bit on potassium's side because it has a little bit bigger memory potential than sodium. A little bigger concentration gradient is really the deal. But you'd expect it to be somewhere in between, whereas if the membrane, and there's other sort of intermediates between this, if the membrane becomes 40 times as permeable to sodium or to potassium as sodium, then all of a sudden I think you're starting to think that potassium is going to start dominating this situation. In most standard neurons, there are huge numbers of potassium leak channels that are open all the time and relatively few sodium, so most of the time potassium is dominating. All right, we didn't get as far as I wanted to get. So I think what we have to do, I don't know anything else to do aside from this, is we're going to have to not have homework due on Monday. So I'm sorry. Homework's going to have to be due on Wednesday because I need to show you how to do this next thing. I can't just say, go do that, right? I mean, you probably could, but I need to give you some practice with that. So what we'll do is we'll have the homework due Wednesday. We will talk about that on Monday. We may even start chapter 4 a little bit on Monday. But homework will be due Wednesday. Sorry for going over.